Okay, so hello everyone. This session that is being recorded is for presenting the 5th episode of the workshop tutorial of OpenFOAM using containers. This episode is about how to use the overlay file system, virtual file systems, to store your results and reduce the amount of files that could be generated by OpenFOAM. So before starting with the episode, I just want to show you a little bit of information about the format of the tutorials. So basically, the orange regions are sections for the user to take hands-on and follow the exercises. In theory, when this is an interactive session, I will be doing with you the ones with the bell, and you will be doing by yourselves the ones with the pencil. But now that it is recorded, then you will be doing everything later at your own time. The rest of the colors do not mean anything, so I'm hiding some information that could be accessed clicking in the arrow. So it's not hidden really, it's just collapsed for better understanding of the nodes. And then there are yellow regions that means nothing and blue regions that means nothing but information surrounded in a specific block just for easier reading. Okay, so let me go back to the index and then go directly to episode 5, the use of overlay file systems. Okay, so this OpenFOAM could generate a large amount of files, especially when you cannot have the collated option. That indeed the collated option was created to deal with this problem. So originally, OpenFOAM was developed in a way that every MPI task of the solver will write results in a specific directory. So task 0 writes results in processor 0, task 1 in processor 1, and there you go. So if you are solving a problem with, let's say, 1,000 cores, then you will have 1,000 subdirectories called processor 0, processor 1, processor 2, etc. And under those subdirectories, all the results. And for each time to be saved, time in terms of the solution, then you will have a time subdirectory within each of these processor folders. That could generate files in the order of millions. And if users have millions of files in our file system, then the metadata server can be overloaded. So this is a big problem. Newer versions of OpenFOAM can handle it with the collated option plus the ioRanks option, but other versions or flavors of OpenFOAM cannot. So why use other versions of flavors? Yeah, indeed, we are encouraging all our users to port all their work to the newer versions to avoid this problem, but that cannot be done for multiple reasons listed here. So if you fall in one of these multiple reasons, then you are then you may have this problem if you save a lot of results. What can Pawsey do to help users? Because again, if this problem happens, it is not just a problem for you overloading the file system, because it is a shared file system. It's a problem for all the users of Pawsey. And indeed, as I said, this problem is a problem that exists in all HPC centers. So what have we done to help our users to avoid this? Well, we have a policy to purge files older than 30 days from scratch, so you cannot accumulate old files. We also set a quota of a maximum of 1 million inodes. That means 1 million files or directories in your scratch space. So that forces users to regularly clean, like process, obtain results, analyze them, and clean. And keep doing this process regularly for not reaching the quota limit. But sometimes users are still in the need of having more than 1 million files in their system. And to solve this issue, well, we plan now to use virtual file systems. This is a suggestion that originally came from Dr. Andrew King from Curtin University. And more or less we have followed his original idea with some modifications. So what is a virtual file system? It is a bit more complicated, but it's, just as a general concept, it is a big file where you can indeed save files in the interior. The good thing with this is that our metadata server of the host file system will only observe a single big file, while you can save all your results inside this big file. So here we make use of a technology called OverlayFS that can work pretty well with Singularity. But there are many other options and technologies about virtual file systems that could be used at a certain point. So this is just an idea that works, but it's not fixed just to that. So far, this is the one that we have observed. It works fine. So what is the logic of using overlay file systems? I mean, what steps are we going to follow to make use of it with OpenFOAM? So the 4 main steps that are in these 4 blocks are basically you start normally your setup of your case, and then your processor 0, 1, etc. subdirectories, you rename them. In this case, we are renaming them as back.processor0, back.processor1, etc. So that means that we are hiding the normal structure of OpenFOAM with these processors, but we still have a space where to save some results in our host file system. So we are going to use these spaces, and these names do not exist anymore, or at least at this point. So then we set up a virtual file system, and indeed not just a single one, but we create the first one, overlay 0, and then we replicate it into overlay 1, 2, 3, 4, etc. And then inside of these overlay files, we define a place where the results are going to be written. In this case, I'm setting a path in this variable inside there, and that path is overlay OpenFOAM run channel 395, which is the name of the case we're going to solve. And inside that path, we create the subdirectory processor0 in the file overlay 0. And the same thing, similar first part of the path, and then processor 1 in overlay 1, processor 2 in overlay 2, etc. Processor 4 in overlay 4. And once we have this space inside the overlay file systems, we write what we had from the initial step in the processor 0, this is a mistake, I need to fix that. Well, what we had in processor 0, we are going to copy it to the interior of overlay 0, processor 0. Then what we had in should be back processor 4, should be copied to the interior of the overlay 4, which has this directory, and then we copy there. So basically, we replicate information that we had outside to the inside of the overlays. So once we have that information inside, then we create the trick to basically trick OpenFOAM to think that it is writing at the normal processor 0, processor 1, 2, etc. directories, but indeed it's going to be writing to the interior of the overlay files. What I mean is we create soft links, in this case the soft link named processor 0, and should be pointing to the interior of the overlay 0, processor 0, and then processor 4 to the interior of the overlay processor 4. So basically with these links, OpenFOAM will try to read and write from processor 0, but indeed that link is pointing towards the interior of the overlays. And that's basically the way we are going to write. And once we have all this setup ready, then we execute the NPI application. This is a bit complicated, but basically, I'm just going to say this. We execute the solver with srun to spawn multiple NPI tasks, and we sort out the run in a way that task 0 mounts the overlay 0, and then it allows to read and write stuff to the 0 structure, and then task 1 mounts the overlay 1 and allows to write in the number 1 structure of files, etc. So let's do some of this hands-on thing. So let's go to the scripts space where we are going to work with the case. So you will need to clone the Git repository for the scripts. So we will give you, or it is already in the notes of the tutorial, how to clone it. Once you have this directory, then we move into the scripts and then move into the 6 episodes. So we do 06 subindex tab to complete all this name. And now we are, okay. I'm sorry, we are not going to do the 6. It is the 5th episode. So we do cd 05, use overlay, etc. And now we are in the 5th episode section. We have another subdirectory called example. So far we only have examples for 2.4.x. So then we move into that section. Now we have the same structure for the other episodes, scripts with A, B, C, D, E, etc. So those are the scripts. And basically the next sections in the tutorial are explanations of these A, B, C, D, E scripts or substeps or whatever you want to call them. The first part is already done. So that first part creates the space for the case, which has been copied from a tutorial that is inside the container. And then we're going to follow through the decomposition and the setup of the overlays. This is the most important part, and how to run the case after the setup. So first part has been pre-executed. We have already our run directory here. Then, okay, so now the decomposition. So what I'm going to do is to execute the script first, and then we will come back to the description of what the script says. So basically, in this case, for this recorded session, we don't have a reservation. So if we type sinfo, we will see that debug queue have some space for nodes are idle. So we're going to use the debug queue instead of the reservation. So anywhere you see the usage of reservation, we're going to swap that, and we're going to use sbatch dash p, which means a partition, and we are going to use the debug queue partition for executing the decompose form. So that's that script has been sent, and we can ask the queue how my job is, well, in what status is my job. So sq-u user will give you the status of all your jobs. There are no jobs in the queue. That means that the job has finished already. So the next command that is listed in the tutorial is basically list what is down there in the case. So we do an ls run. Down there is the case channel 395, and we have processor, many processor directories there. So down there in the case directory, channel 395, let me do an ls of just that directory. Run channel 395. So in channel 395, that's the case directory. We have the initial conditions, we have all this common structure for OpenFOAM, and the decomposition has already been done. So we have processor 0, processor 1, up to processor 4. And if we do the command, then we go with the up arrow to the previous commands. If we just list what is inside all these processor directories, we see that the composition has been done already. We have initial conditions and the mesh definition for each of the subdomains that are going to be solved in parallel. So that's the script, and it is basically the same kind of a script for previous episodes. It's so I will skip the description of the script, and I will go directly to the setup of overlay. So again, I'm going to execute script C. So let me remove the slurm output that I have already there. I know everything went fine. I can get rid of this file. And we're going to execute the script C, which is setup overlay. I'm sorry, the notes, I changed the name of this, but it is basically, in the notes it says C prepare overlay. And in the final version of these scripts, I've modified the name to C setup overlay phone. But that's the one we are going to execute. So again, dispatch partition debug queue C tab. Anyway, we are doing all the time C.tab and whatever the name it is. So now we're going to use execute the setup for the overlays. So let me well, let's check the status of the job. Sq -u user. So it is running. We can see the output if we use tail -f slurm whatever the job ID this job has. And well, we were not able to see it running because the job is already finished, but there is a message script is done there. To exit tail -f, we can do Control-C. And then we can even check what is the status of the job. There's no job there anymore. So the setup is being done. So let's go to the case directory. Let's explore it over there. So cd run channel 395. And then you'll see here that all the processor 0, 1, 2, 3 have been renamed. And the information is still there. So if we ls back.processor, all the processors. So those directories have just been renamed. And we have all these overlay files that are big files, 1 gigabyte of size, overlay 0, 1, 2, 3, 4, and that is the place we are going to use to write our results. But we cannot see inside of them unless we mount them. So what we can do is to use Singularity to read the files and see what is inside of them. So what we are going to do is to module load Singularity, then define the image we are going to use. So the image is in the Pawsey repository, so it's group Singularity Pawsey repository OpenFOAM 2.4.x. That's the image we're going to use. And then just let me define another variable, which is the path that we define inside of each of these overlay file systems. So that's a common path. So I'm calling it that inside there equals, let me just copy paste this part, equals overlay OpenFOAM run channel 395. This is completely arbitrary. I thought this was a good structure to define inside the overlays. Some sort of normal OpenFOAM structure and then the name of the case. And below that, we are saving our results. So that's the path. And now I execute Singularity exec the image. I'm sorry, exec. I'm going to mount an overlay file system. I cannot see the 5 of them at the same time, but I'm going to take a look into what is inside overlay 1. So I say -- overlay 1, and then I'm running the image. And then I can execute the command and say, what is inside, list me the content in a common path inside here, and then inside processor 1. So we only have processor 1 inside overlay 1. We don't have processor 0, that's inside overlay 0. So now I'm listing the content inside the overlay, and we have the replica of the files that were originally created with the decomposer. And well, as I said, we don't have processor 0 here. It will complain no such file or directory. So how we did it? Let me expand here, and we have here the script. Well, pieces of the script. First of all, in the header, you will see that I'm using for this script 4 tasks. This number is independent of the number of subdomains for OpenFOAM, which for this tutorial channel 395 for version 2.4.x, the tutorial uses 5 subdomains. So I'm setting this to 4, and this is just basically the amount of cores I'm going to use to copy files. So if we have 1,000 cores, then we can possibly use, I don't know, the whole node, 28 cores for doing all this copying in and out. So for accelerate a bit this copy and transfer of files tasks. So in this case, I'm using 4 tasks for doing all these copies. Then, instead of mounting, instead of loading the module Singularity and some other settings, what I'm doing is sourcing these 2 scripts that are in the same subdirectory. So in my terminal window, let me go back 2 levels up where the scripts are. So you can see we have this A, B, C, D, E, but we have also case settings, foam, and image settings, Singularity. So inside the script, and that is happening inside all of these scripts, I'm sourcing these 2 other scripts. So basically, I'm using these 2 other scripts for general setup. That is going to be a repetition for all the scripts. And if I need to make a change, I only make that change in these 2 scripts, and that will propagate to all the scripts. Okay, so the first one, the image setting Singularity, has settings for Singularity. So let me expand the section here. And this is what this one has. It has the module load Singularity. It has the definition of which image we're going to be using, and also has the definition of the size of the overlays. So this size is in gigabytes. I'm saving, or I'm using this variable to be understood as an amount in gigabytes for the size of the overlay file systems. And the size you need to use depends completely on your case. Basically, it should be big enough to be able to keep all the files inside, basically in a one-to-one translation. So if you need 1 gigabyte of space or 100 gigabytes of space to save your results for a single subdomain, then you set this to 100. So you need to do the maths of how much space you need. And the other script is for the OpenFOAM settings. So basically, what is there here? Okay, this first part, I think, is for the tutorial setup. So what is the name of the case that we're going to be working in? Then settings of this inside dir path for the overlays. How are we going to be naming that? What is happening here? Okay, it's difficult to see where is the end of this collapse section, but it is just these two blocks. So name of the case directory and name of the inside dir. Basically, that's what I'm setting inside these settings. Now, okay, so basically number of tasks that are going to be used for copying, basic settings, and then all the process. So because in the previous script, in the script B decompose form, the decomposition was done. Here in the settings for overlay, the first thing we do is the renaming. So every processor directory is going to be renamed as back processor directory. Then the creation of the first overlay. So all these syntax Marco explained in the webinars for containers, how to create an overlay file system. So basically we are using the same recipe, and this recipe is documented in the Singularity documentation. So here is this variable is in gigabytes. So we do the multiplication to put the count size in bytes, and then do the execution of the creation of the overlay. Once we have the overlays, we do the copy. So as you can see, I'm doing srun dash lowercase n1 dash big case n1. So this means srun in a single task in a single node. And then these two parameters are needed for being able to execute all these several sruns at the same time without an issue. So basically, these are parameters for srun to execute this command, the copy of the overlay 0 into overlay 1, 2, 3, whatever. And that is executed in the background. So this allows to execute several of these commands at the same time. So if you see there is a for here, and then this thing executes, in this case, 5 times this command. And then we have a command here that says wait for all the background processes to finish. So basically, all these copies will be executed in the 4 tasks that I set up for this script at the in the header of the script with dispatch. Okay, so after replicating the overlays, then we create the files, the directories inside the overlays with a similar structure. So okay, srun Singularity exec overlay, and which overlay is going to be mounted is the corresponding one for these 4 cycles. So mounting overlay 1, we are going to create processor 1, overlay 2, processor 2, etc. all at the same time in the background, and wait for them to finish. And then similar command, but now once we have the directories inside the overlays, we copy all the content that we had in the back processor 0, 1, 2, 3 to the interior of the overlays to this path inside dir processor 0, 1, 2, 3, etc. At the end, the last step in the script is just to check what is inside the overlay 0 processor 0 structure. It's just a checking, and you can see that content in your log file instead of checking manually. Thank you. So good. So just to remind you what we have. So CD, let's go to the case again. Okay, so we have this structure. What is missing still is to create the links that are going to be pointing to the interior of these overlays. And once we have those links, we can execute the solver. So let me again go back 2 levels. We have the scripts here. And now I'm going to show you the script before executing. So now we have the the script for execution. So in this script, I need 5 tasks because now it is the time for executing the solver. Then there are several settings that are similar, so I'm skipping them. I'm jumping up to section 5 in the script. These are OpenFOAM settings, similar to previous episodes. This section 7 is the one that creates the soft links. So basically, again, it's a cycle for all the as many as subdomains we have. We do a cycle with the variable $i. And again, we execute a command that is going to be executed like many times at the same time in the background. And basically is create a link named processor 0 that is going to point to the interior of the overlay 0. And the interior of the overlay 0 is found in this path. So initially, these links are going to be broken in the host file system. But once we mount the overlay 0, then that link will be functional. The link to that goes from processor 0 link. And once we mount processor 4, overlay 4, then the link 4 is going to be functional. So we create the links, and then we execute the solver. So now, for the solver execution, there is this particular way of writing the command. So basically, instead of having, after the srun options, having immediately the Singularity exec, what we are doing here is putting the Singularity exec command as an argument to the bash-c command. So basically, what we are doing is bash-c is receiving the command, but with this trick, and in single quotes, this variable slurm proc ID or process ID is going to be evaluated inside the srun execution. So this variable does not exist in the host file system, only exists after executing the srun. But the trick allows us to execute Singularity and tell that for task 0, it's going to mount overlay 0, and for task 1, overlay 1, etc. So that's what we need. There is no other way we have found to do this. So it is a bit cumbersome, but I think, well, it's a way we have found, and I think it's understandable. So basically, this Singularity exec is going to mount, when we are dealing with slurm process 0, it's going to mount overlay 0. Once overlay 0 is mounted, then we'll mount it for the image that we are going to work with. And again, because this variable, the image, is not a global variable, we need to go out of the single quotes and go into a double quotes section just to evaluate the image in the host. And then we need to go out from this double quote section and come back into single quote. I think this is not strictly necessary. We could have the double quote section up to the end. It doesn't matter. The place where we needed the single quote section was just to evaluate slurm proc ID after srun was run. So basically that's it. So once srun spawns all these processes, Singularity allows them to communicate via MPI libraries, and OpenFOAM will work fine. And each of them will have their corresponding overlay file mounted. So let me remove this LARM file for the setup. We know it's fine, and let's execute. So sbatch partition debug q d run form. So we are executing now. Let's check the status. sq-user. It's running, and now we can. So now we have the output, and now we can use tail-f slurm job ID output. Okay. Okay. Which one I executed? Listing of times side overlay 0, script done. Okay, it was really short. So let's see our case directory again. Let's explore them. Okay, now what we see is that the script created these links. So these links, processor 0 is pointing to a path that is only recognizable inside overlay 0. And right now, the color indicates that this link is broken. So I mean, we cannot move to processor 0 from here. Processor 0, it doesn't exist. So the link is broken in the host file system, but there should be results inside. So to see the results inside, we need to do it by mounting the overlay. So let's see what results are in overlay 4. For that, we can do Singularity exec --overlay 4, execute the image, and then ls and the structure of the interior directory processor 4. So now we are listing the results inside processor 4, and we have all these results already inside there. So we are saving all these files. So these are just time directories. Inside each of them, let's list what is inside the directory 9.8. Inside each of them, we have the result files. So it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 files per time step. Then you multiply that times to all the time steps we have, and then multiply that times the number of subdomains, and that's the way the number of files builds up. But now, here, really in our host file system, we only have these 5 files for the results. And then we have, I'm sorry, these are the links. So these 5 links, these 5 files, and some files inside the processor 0, 1, 2, 3, etc. So that's it. Cool, isn't it? Any questions, Basha?
Yeah, I have a question, not related to the files itself. I see there are like 13 variables here for each case file, for each time step.
That's
so, yeah. So this is default mode of writing the files to the from the OpenFOAM, I think so.
Yeah, that's also one of the issues why OpenFOAM generates that many result files. So it doesn't put the results of all these variables into a single file. It is single file per variable. Then
yeah, but in practice,
Yeah, in practice, well,
we don't need all those for post-processing. We only the one.
Oh yeah. In practice, possibly you are just interested in one of them. Yeah. You're very right.
So that has to be done in the OpenFOAM setup case.
Okay. So yeah, you decide. You can decide which variables to save, but basically, I think you need to keep saving the variables, because if you want to restart the case from this point, you need the status of all these variables to start with.
User has to decide what time step he has to save it and what results he want, without keeping the process without keeping it open to save optimize the memory.
Yeah, exactly. So user decides which variables to solve, which variables to write out, and the frequency of saving. Yeah. Okay. So in this case, indeed, the frequency of saving from the tutorial has been modified just to generate a decent amount of files for the exercise. I guess the frequency was indeed a bit lower, but so in the scripts modify the original frequency to write a lot of files just for the testing, and yeah, but that's all user decision. Yeah.
But general note, those who are solving transient problem, this might be the one of the potential problem area for them. For those who are solving steady state, they don't have to worry about generating a lot of files in the systems.
Yeah, exactly. If you are solving steady state, then you just save every, let's say, if your case, even in steady state, will need to run for 24 hours in Magnus, then let's say, just not for losing your results, if something happens with the computer, you could be saving with a frequency of every half an hour execution time, calculated by your own experience with the case. So let's say every 2,000 iterations, save something just to have something in case the computer fails, and then you finish with 48 savings, or every hour you finish with 24 savings, or every 2 hours, whatever you consider a decent checkout point. But in theory, you don't need to save anything, only the final solution if you are in steady state. Yep.
Yeah, thank you.
Okay. Yeah, but the main problem appears with the transient solutions, because in transient solutions, usually you are interested in every time. Well, not in every time, but with a more frequent and a more longer amount of times to be saved. Usually not every time step, for sure. Sorry. So what we have here. Yeah. So yeah, now what can we do with the results? So the results are there, but are inside the overlays. So we have this problem with the reconstruction. The problem with the reconstruction is that the reconstruct bar tool is single-threaded and needs to be able to see everything inside the processor 0, 1, 2, 3 directories. And we cannot mount many overlays into a single Singularity instance or container. So there's no other way but taking out the results from the overlays to the host file system. So basically the idea is take out what you need only, not everything, because at the end, if we do if we copy out everything, then we will finish with the same original problem. So just copy out what you need, post-process it, and remove it. And there's no problem with deleting it because you still have it inside the overlays. If you need it again, you copy it again out. That's a bit of the price we need to pay for reducing the amount of files with OpenFOAM versions that do not have the collated option. So, and if you need everything, then copy bits, post-process it, remove, copy the next, post-process it, remove, etc. So that's the idea. So here the script for the reconstruction, what it will do is the following. So again, even if the reconstruction is single-threaded, I'm asking for more than one. I'm asking here for 4 tasks. Again, these 4 tasks are going to be used just for doing all the copying. And I'm saying I'm going to reconstruct time 10. And then what the command does is execute Singularity, mount the corresponding overlay file, and make a copy in this cycle, make a copy from what is inside the processor I. Let's say II is 0, so mounting overlay 0, what is inside processor 0 inside overlay, and copy the reconstruction time, that is the time 10, and copy it back to back.processor 0. Then when we are dealing with 1, we mount overlay 1, we look inside processor 1, we copy time 10 into back processor 1, etc. So then all these results for time 10 will appear in back, processor 0, 1, 2, 3, 4. Then we do the opposite. Instead of, we create soft links that instead of pointing to the interior of the overlays are going to be pointing to these directories that we renamed. And OpenFOAM will try to look for something in processor 0, 1, 2, 3, and indeed it's going to be reading or writing to these renamed subdirectories. So it's the same trick. And once we have the links, we execute the reconstructor just in a single task, in a single node, reconstruct, and it will see the results there and we'll be able to reconstruct. So we can do that from the scripts. We see the 2 levels above where the scripts are, and we sbatch the partition debug queue, because we don't have reservation here. Reconstruct overlay from overlay. And we can do queue -boom user. To see the status, it is running. It's finished. Now we can go again to the case directory and see that we have already here the reconstructive time 10. So we can go to 10 and see all the results files. But instead of being all these results spread into 5 subdirectories, they have been merged. And now we have a complete result reconstructed in time 10. We can see also inside back processor, where cd back dot processor 0. We can list, and there is the extracted decomposed piece. So what is missing here, I should add that part. What is missing is the removal of this time 10 inside the back processors, because we already have a reconstructed case. But this is just a first informative script that can be modified for later use. And this is still a bit, how to say, a bit in a first stage. In a real case scenario, we may need a bit more elaborated scripts to do the reconstruction in batches of many times and deletion of the files that we don't need anymore. And I think that's it.
All right. Thank you very much, Alexis.